Okay, it's my goal to record all of these with the screen shared. So if I don't do it at the beginning of class, someone please remind me to start the Zoom and start the recording, and so on. And I'm sorry, your name? Hayden. Don't be sorry. Okay. Okay, so 6 people today, 3 CS528, CS350. The two courses go pretty well together. CS350 is really a modeling and simulation course. And so we'll cover a lot of generic modeling and simulation terms and processes. However, the most, in my opinion, interesting models and simulations are agent-based simulations. So CS528 is agent-based systems, not agent-based simulations, but agent-based systems. And if we're talking about building a simulation that involves agents, which every one of you will do this semester, then you're learning about agent-based systems. That's the plan. Standard syllabus stuff. I don't know that there's that much to go over. Everybody likes to talk about grades, but let's see. Okay, so for the outcomes, what we'll do is, like I said, we'll start out with just introducing you to modeling and simulation terminology and definitions, and then build into how do you design an experiment, how do you do validation, verification of a model, how do you do verification of a simulation, how do you write test cases, that kind of thing. So that all speaks to the modeling and simulation. Because we're going to be focused on agent-based simulations, then the CS528 people get their agent information as well. Okay. There's actually one paper. I've got a bunch of papers that instead of a textbook, and they're getting dated. I do need to update some maybe, but they're really good at what they're doing. So, and there's one paper that's all about agent-based simulations that I think is really just a great synopsis of agent-based systems in general. Grade breakdown, as you would expect, 90% is an A and 80% is a B. I'm a computer scientist, so I do integer-based math, so that means there's no fractions, right? So if there's 1,000 points and you get 900, then that's an A. If you get 899, that's a B. For the CS528 people, there's an additional 200 points because I want you to, in addition to the report that you're going to write for your project, write a paper with the intention of submitting it to a conference or a journal. So when we start to talk about, hey, what do I want to do for my simulation? That's great if you want to do some kind of a village survival game, but that's probably not publishable. So maybe we'll talk about what can you do that's published. And I know some of you guys are already working with other faculty members, and if you can fold what you do in this class with the work that you're doing with other faculty members, the work that you're doing on your research, the work that you're doing for your thesis, all the better. We had last summer, someone did exactly that. They were working with Dr. Ochoa and working with language models and working with how do you get good responses from large language models like ChatGPT. So this person was building a simulator where they just hammered the large language models and just tried to evolve good prompts. So I think that's fairly straightforward. There's no tests, no exams in the class. However, I have 6 project assignments plus a presentation at the end of the semester for the project. And I have, I think, 8 homework assignments. And so the 8 homework assignments, 50 points each. Generally, that's going to be 5 questions, 10 points each, generally. So 50 points each. And then that adds up to 400 points. And then the project deliverables are all 100 points each, except the first is only 25 and the presentation is 75. That's where I get my last 100th. And so the first one is really cheap, 25 points, because it's basically your project proposal. Hey, here's what I want to do. We'll have lecture in here. Like I said, I'll have Zoom up, so I'm sharing the screen, which should be recorded, recording my audio. Hopefully it'll pick everything up, hopefully. I'm not doing the smart AI thing. You think I should? You know, the summary thing? Maybe as an exam, maybe as an experiment. I know some of y'all have points in time over the semester where you may not be able to be here, and that's one of the reasons I'm doing it. So we have some flexibility with that, and you have a record. You know, I'll once this thing turns everything into a video, I'll post it somewhere, either on Canvas or on YouTube or somewhere. Questions? Okay.
I was just going to say, if you're going to try to utilize that, most likely the mic and your laptops might. Unless you're like right in front.
Right, yeah, and I tend to wander, but I'm going to try to stay near it. Yeah, but if we have questions like that, I should get in the habit of repeating the question, right? So the comment was, is the laptop mic good enough? Generally, I've had good success with it, but there's no guarantee. Past performance is no guarantee of future behavior. Yes.
Parties afterwards, or can you join us in live?
Yeah, so I didn't know if it was valuable for people to join the Zoom live if they're not here. If you want, I can publish the link on the Canvas page and then people can join in. So, yeah. My biggest problem with that is usually someone will ask a question in chat and I'll forget. So you guys will have to remind me that, hey, someone asked a question in chat. Other questions? Turn in your homework by midnight of the due date. I'll accept it late, half credit. If it's late by like, oh, the next day, you know, we'll work that out, right? If it's something, you know, my car broke down and so I couldn't turn it in today, that kind of thing. Large language models, as you know, or probably are aware, you know, we don't know what the heck to do with large language models, with ChatGPT, Gemini, all those other tools. The assumption here is that that they will be used. That's my assumption. They will be used. So now we just have to figure out how to use them ethically, which means you don't ask it to write your paper for you. You don't ask it a question and then just cut and paste what the solutions are. And learning how to write good prompts is a skill. It's a brand new skill that we all need to learn. It's gone beyond. It's gone well beyond. In Google, you know, if you typed a whole sentence for a question, it didn't care. It picked like 3 keywords and then just gave you anything with those keywords. Right? Outlook is worse. Like if you type in CS228 on your mail, search for CS528 on your mail, it'll give you everything with CS and everything with 528. Yeah, so you have to learn tricks to tell it, no, I want both of those things. Okay. That's it, right? Let's talk about project for a little bit. So I have one page for the project assignment, and what I'll do is keep adding. Like I said, I've got like 6 deliverables plus the presentation, and there's the rough form of it. And so I've done, you know, the actual assignment. Phase 1 is these sections refer to sections in a document. I'm going to show you in a second. It says, hey, you know, this is your job. For phase 1, fill this stuff out. Here's how many points you get for each part. Quality of writing does count. So what I like about having 7 students in the class instead of 70 is I can actually sit down with you guys and give you hopefully good advice about how to write this stuff. It's very It's very rare that we have someone graduate at the undergraduate level who really is good at writing, because we just don't have the opportunity to focus on that much, right? Especially, you know, in engineering, you guys are all worried about, you know, differentials, right? Integrations, and then writing. Who's in the undergrad class? CS350? Okay. Have you taken tech writing yet?
I'm not allowed to.
What, you're not allowed to?
No, the military credits that, they say substituted.
Oh.
Writing an after action report is not the same as a
There you
pen
go.
paper.
That's true. It's a form of tech writing, I guess. It's got jargon, right? A lot of jargon. So the different phases will come in, and then, you know, with just a normal project deliverable, we're going to build it up in stages. And so about every week, and this is really the biggest challenge of this course. This would be great if I could have done this course over like summer C, so it lasted 12 weeks, just so you would have time to do the project. But I predict the number of people who would do that would be 0 students would sign up for that class, right? Because everyone wants either summer A or summer B, but not both. I don't know. You're here all summer. Maybe you would have signed up for that class. So that is a challenge that I acknowledge, that getting an experiment done in 6 weeks, up and running, designed, tested, validated, and then getting experimental results is can be tricky. So we'll start out though with, hey, just let me show you the document here. You'll start out with just, here's the introduction and here's some research questions. And basically what you're asking me is, hey, this is my proposal. This is what I want to do for my simulation. This is the kind of simulation I'm interested in. And my only restriction is let's make it agent based. So no digital wind tunnels. Sorry. Then the next section is to fill in the background material. So then again, this is about every week, right? So after you turn in your first part, then next week you're going to fill in the background section. The background section, the cleanest definition of a background section in any document is you should put all the information in there that a reader needs to know to understand what you're doing once you start telling them what you're actually doing, right? So if you're going to do some kind of a queuing model, you know, where people are lining up at the bank to get service from a teller, then you have to put all your formulas and all the theory about queuing model and stuff in the background section. Later on, you're going to talk about your specific simulation, your specific experiment. But in the beginning, you have to tell people what the terminology is that they need to know to understand your work. The next week, we go into simulation design and experiment design. So now you're going to say, okay, now that I've defined my problem, here's how I'm going to make a simulation to do some experimentation with this problem. And the experiment design, we have lectures on that, is about, you know, how do you create an experiment? There's different ways to do that. You have all these different variables that you may be interested in. How do you manipulate them in a way that is both gets you good coverage or even full coverage of all the different variations, and helps you understand the effects that each of those changes in variables that contributes to the result. Then we start building actually software. So now that you've got your design, then you start building. So this is build, program. If you want to use some kind of a simulation tool, like some of you guys may be very familiar with MATLAB. MATLAB is a very good simulation suite. Go for it. You want to use something else, Python, whatever you're comfortable with. You want to use Unity? It's fine. I don't care what you use. So whatever your strength is, you can go for that. But this is where you're actually doing programming. You might program from scratch. You might use a simulation tool. Yeah.
Or what about ROS?
I'm not familiar. So,
Robot operating system.
oh, okay, yeah.
What they teach in robotics.
Um,
Better.
If you can create a simulation using that, that'd be great.
Like a robot in a room, trying to figure it out.
Yeah.
That's basically
But
what it's designed for.
okay, but then can it also, within a simulation, can you construct the environment as well as the robot?
You can definitely send it to a full on obstacle.
Okay. Then, yeah, that would be fine. And again, since we're doing agent-based stuff, the ideal thing there is you have multiple robots interacting with each other, because that's where you get really good behaviors. Yes.
So exactly.
For the grad version of the course, can we write the final report like as the publication ready paper to kind of?
Yeah, and that's actually the plan, right? So if you're in the grad level course and I want you to do this publication paper ready, keep that in mind while you're writing your document, because if you write it in such a way that it's basically publication ready, you're just cut and paste
Into the template. Into the actual template, yeah.
Yep. And the template that I have for the report is similar to how you might want to write a conference paper anyway.
Okay.
Now that you're building some software, and you're not going to build it all at once, generally, so you build some software, and we're going to look at some interim results, and now you're going to do your little mini test to make sure you build the thing right? So you do some verification, maybe some validation, and then you hopefully by this point you get to complete your simulation, and then that gives you a week to actually run your experiments and talk about results. Try to figure out what the results are. So a normal progression, but squished into a fairly nice time frame. So we just have to be really careful when you choose your topics, that it's interesting enough to be non-trivial, and yet it's simple enough that in a 6-week time frame you have a good chance at getting it done. When I talk about these different phases, so for example, in this in the first assignment, I'm saying section 1, section 2. What I'm referring to is in the project template, I'm giving you a template to help you out, hopefully help you out. And I'm letting you know for each section what's supposed to go in. Introduction generally has some kind of a wishy-washy, feel-goody motherhood statement about how great everything's going to be because of this research, and then you follow up with just a really generic description of, hey, this is a topic that people seem to be interested in, here's why they're interested in it, and here's what I'm going to investigate. Then the research question, and there we want an actual honest-to-gosh research hypothesis, right? Something that can be proven to be false, or statistically likely to be false. Then we enter the background section, and as I said, the background section is basically everything that the reader needs to know to understand your simulation, to understand your model, understand your experiment. Right? You haven't got none of the experiment design yet. You haven't explained the model that you're using yet. You're giving the real world situation. So it might be, like you want to look at robots is a simulation, but what's the real world model? Oh, okay, in the future there may be robotic cars that have to negotiate how to get through an intersection together, whatever, right? You've got some kind of a real world thing, or theoretical real world thing that does not relate specifically to your experiment, and then you're going to explain how your experiment addresses that thing or explores that thing. Or in the case of robotics, people have been studying this for a while now. This whole thing with human robotic teams, right? So now historically we've always had human teams. Now we're getting into human robotic teams, and how does that work out? People are playing with dialing up and down how much initiative the robot has. Does the human always have to tell the robot exactly what to do? Or can the robot do stuff on its own and initiate its own actions? And then, which is normally what you do with another human, right? Is, you both know the job after a while. You both know what needs to be done, so you start doing it. Or should the robot be in charge? Should the humans start to take orders from the robots, right? So people have been playing around with how does that look? The robotic vehicle and the army truck and a farmer with an ox cart shows up at a three-way intersection at the same time, and who goes first, right? How do they resolve that? Those kinds of questions. Then you get into the actual, your specific model, your specific simulation. We'll talk about the model, modeling in a little bit. Verification and validation. So we don't have a lot, again, this is because we're on such a compressed schedule. This is not going to take a large part of your time, but let's get some good warm tummy feel goods that, you know, what you build is reasonable. That it's doing what you thought you wanted it to do. And then that's what verification is. Validation is about, does it have any kind of real relevance to the real world? You know, so in the real world, I don't know, if the building catches on fire, people tend to leave the building, right? So if your human agents in the model run into the building and purposely try to get burned up, probably not a good valid model, right? That's probably not a good model of human behavior. Then the experiment design, which is, okay, now I'm going to run 1, 2, 5, 10, whatever scenarios. And based on these scenarios, I'm going to start to fiddle around with my variables and find out what happens. Then you can report the experimental results. So that's basically the project cycle. And then whenever you're publishing, you tend to do a section on related work. You're never the only person in the world working on these things. So then you can say, oh, so-and-so also did a similar thing, but they did it differently than I did. They included, when the building caught fire, all the agents stayed the same. And in my model, everybody went into panic mode. So I added a new feature, right? That kind of thing. So you look at what are other people doing and compare and contrast. You hopefully have already done that anyway, because in order to prepare for this, you know, you're not going to build a model out of thin air. You're going to say, oh, let's look at what other people are doing and get an idea from there. And then from there, I can get a sense of what I want to do. And then, of course, conclusions, which is basically you want to answer those questions. Remember, you had some questions at the beginning. Answer those questions. And then what would I like to do in the future? How could I extend this thing? Research generally is considered valuable only if there's a way that it can be extended. Most people don't like a dead-end research. And then normal referencing and citations. This school teaches, what's it called? The psych people use it for a citation model. APA. In engineering, we're not that fond of APA. I don't care if you use it, but there are other citation styles, better citation styles, in my opinion. And so I don't really care which one you use. What I do care about is that you do your referencing and citation properly. And the distinction that I have is a reference is a list of the document where you got some information from. The citation is somewhere in your text you use that information and you put a note there, right? Whether it's APA style or IEEE style or something, or Chicago style or whatever. So the referencing is just, here's the document, and then up in your text, I should be able to find out where you use that document, and it should be applicable, right? If you had a particular piece of information that you said came from that document, I should be able to go to that document and find that specific piece of information. In addition to the project, in order to do some planning and make sure that you're not just, flailing around, I'm going to ask you for every deliverable to turn in this backlog document, this kind of a planning document. So when you turn in your first phase 1, then you're going to say, okay, for the next week, here's what I have to do. And then you and I get to agree. It's almost like a little contract. You and I get to agree. Okay, yeah, that makes sense. That's what you should be doing. And then estimate how many hours it's going to take you to do that. And then leave that percent done blank, because you haven't done anything yet, right? So then when you turn in number 2, then you fill in your percent dones. And if they're all done, then you don't have to worry about them. If they're not done, then repeat them down here with a smaller estimate, right? How much work is left? And then you also say, okay, and in addition to finishing up that work, I'm gonna do more new stuff. Add rows as needed. And the whole point is, again, so that you aren't sitting around thinking, I'm not sure how to do this. I don't know what to do next. Right? You get if you do it right, you put these down into nice bite-sized chunks, get that stuff done. When I taught this before, I was throwing out the Agile Scrum model, but it's not that useful in this class because we're not working in teams. And the majority of people have never been exposed to Agile Scrum, so there's no value to it. All right, so those are the three documents that are associated with the project. And I put the first project assignment up due next Monday. And so if you look on Canvas, you should see it due next Monday, and you should see these three documents up there. Are there questions about that? Okay. And I wanted to go on fairly long about that because, you know, it's a big hunk of your grade. I've been saying agent based, so let's clarify what that means first of all. What's an agent? Any thoughts?
I'm gonna just use game terms. It's basically a entity or NPC that's able to perform some kind of action in the environment.
Okay. We're going to modify that just a slight amount.
And react to the environment.
Yeah, now you're getting where I want to go. Yeah. Right. So a door performs an action, or a hammer performs an action, but it is always being directed by something else. So what distinguishes the agent is that it makes a choice. So agents are things that choose, and the reaction is a choice. Which means, by the way, that simple definition covers a lot of territory. And we're going to have all kinds of definitions about how agents are built and what it may mean and what their complexity is. The simplest agent is basically a coin flip, right? If I flip a coin, I'm either going to go to the movies or I'm going to go to the lake. Oh, okay, I made a decision, right? The coin made the decision. So you can have really stupid, simple agents. Basically, am I going to do something or not? Random number generator. Or you can have really complex agents. They have some kind of AI embedded within them. They have maybe a rule-based structure or a neural net input-output system. Maybe they have memory, so they know their past decisions and can track how well those worked out to influence their future decisions. Maybe they are able to plan, so they're able to lay out in the future. Okay, I'm going to do this now, but then I'm going to do this, then I'm going to do this, then I'm going to do this, right? So these are much more sophisticated agents. It turns out you can do a lot of really interesting things with stupid agents. Stupid agents that say, am I going to, you know, I've got a light bulb. Am I going to turn on my light bulb or not? Yes or no? And the reason is, if you get multiple agents in the same simulation, in the same environment in the real world, you get interaction between the agents. And that's where the real fun starts, because you get something called emergent behavior. Difficult to predict, difficult to capture, difficult to formalize. But really interesting stuff. And people are studying this like crazy now. We steal a lot these days from the biological world. So you may have heard the term ant logic. Ant colonies are very robust. They can do amazing things. They don't drown. An individual ant can drown. An individual ant can starve. It's hard for an ant colony to starve. And they do it not by having like a super brained ant that's in charge of everything. They do it through interaction with each other. And they're always just dropping these little chemical trails, right? Little pheromones, dropping it from, it's too hot, drop one of those. Too cold, drop one of those. I'm hungry, drop one of those, right? And then the other ants will come along and respond to that. So if a lot of ants are dropping the I'm hungry pheromone, some of the ants will go, you know what, I'm going to go look for some food. And they respond to that. And they're kind of programmed, like they don't really, it's not like choice, like the way you and I think of choice. It's just, they have some threshold level where when they hit that chemical scent, off they go, they're going to look for food. Ants, if the colony is too cold in the nursery, some of them will go up and lay in the sun and warm their bodies up and then come down and transfer that heat to the nursery. That's pretty clever. Did they decide to do that? No, that's all with interaction. So what you can get through stupid, simple examples is individual behaviors. Through interaction, you can get really complex behavior and robust behavior. And that's what people are studying in terms of cybersecurity systems, robust software systems that are really hard to crash, multiprocessor systems that interact together. There's been around all kinds of algorithms for a long time with multiprocessor systems of who gets to send a message now. And so some of those systems are, you actually have one processor in charge. Okay, it's your turn, it's your turn, it's your turn, it's your turn, right? But what happens when that processor dies? Well, then all the other processors figure out, oh, we haven't heard from that guy for a while. And then they go into a voting mode and they actually will vote and get consensus to who the new leader is. Right? So there's all these very interesting interaction things. The stuff that's happening now, though, again, is based more on stealing from nature and trying to figure out, like in an ant colony, if an ant's sick, the other ants can detect that and they will like drag that ant away. Like, we don't want you in the colony anymore. Can that be used or modeled in such a way that if you have a bunch of computers on a network and one of them is infected with a virus, can you detect it and then cut that one off? Those kinds of questions are being researched. In fact, Dr. Watson in our department is doing a lot of work with that. There's all kinds of things about that. There's also doing work using the similar logic to try to do efficient distribution of firefighting personnel and equipment in large forest fires. Not through some person who's got 40 years experience saying, oh, you guys should go over there, but through this interaction of agents. So that's what an agent is. It's a decision. And again, they can be stupid simple or they can be complex. Oh, one more example of stupid simple. Have you ever heard of Conway's Game of Life? You've heard of Conway's Game of Life. Okay, so it's a 2D grid of squares, and the squares can either be on or off, right? Alive or dead. So let's say if they're alive, they're green. If they're dead, they're blank. And so there's like 3 or 4 rules, and the 3 or 4 rules are if there was only 1 or 0 other alive entities next to me, I'm going to go dead. If there's more than 3, I'm going to go dead. If there's 2 or 3, I'll stay alive. If I'm already dead, I'll become alive. And from that simple rule base, and those are probably not exactly the right rules, but you get the idea. From that simple rule base, you can actually construct any computational system in the world, and what we call Turing computable. In other words, anything that this computer can do, that simple system can do. Nobody wants to, right? It's like annoying as hell. But the idea that from that simple interaction, you can get, you can resolve any computational problem is pretty fascinating. Like I said, nobody wants to because it's annoying. What people do want to do, which is fun sometimes, is you go to a Conway's Game of Life site and they'll have patterns. And when you start out with certain patterns, then these different patterns will produce behaviors on the screen. One thing that people get interested in is how fast can you make the whole screen go fill up, right? Or fill up with like every other dot kind of stuff. So when people try to figure out initial patterns that will, in the most rapid sense, fill up the whole screen. Things like that. So that's what I mean by an agent. So the agent can be stupid simple, or the agent can be really complex. So if you have like your robotic agent, your robotic agent might be fairly complex, but it doesn't have to be. You might have some stupid simple robotic agent and get the good behavior through the interactions. So start thinking about, oh, hey, well, what kind of stuff would be of interest? Like, do you have any thoughts immediately of what kind of simulation you might be interested in producing? We've got, Alex says,
I've been doing research in advanced air mobility, so possibly having the like eVTOL autonomous aircraft be agents in like an environment filled with corridors, merging points, and intersections, and seeing how they react to like wind or each other,
right?
making sure that they behave correctly in those.
Is this part of Stansberg's work or somebody else?
Omar, stuff I'm doing.
Okay. So last year, Jeremy Mogg, I think you know, did something like that with he had a human-driven helicopter flying straight and level in his simulation, and then he had a drone just coming at it from different angles. And he was investigating, like when you have two humans in an aircraft and they're flying towards each other, there's rules about how to avoid. There's supposed to be rules.
I'm sorry, man. I played chicken with this with the Japanese CA47. All right, there are no rules.
There's supposed to be rules, but he was exploring what is a good rule set. What is a good robust rule set that would make sense here, and everybody stays within bounds of the flight corridor that they're supposed to be in. Those kinds of things. Other people are looking at, like, can you just layer out the airspace and try to figure out who's supposed to stay where. So think through things like that, right? So you're looking at airspace, drones in airspace.
Just really quickly, what was the project you said that was using like LLMs with the simulations?
That was, you'll have to talk to Lynn Vanderhoff.
Lynn did that?
Yeah. Yeah. And it took her like half the semester to explain to me what the heck she was doing. Okay. But my recollection, dumbed down, was basically she was trying to use I think a GA approach to develop good prompts and get feedback. And what she was doing, I was like, well, how do you measure success? There's got to be a measurement. So there's actually ways to measure text similarity. And so she was taking like standardized, here's what a good article about, I don't know, how do you make cloth is about. And then here's my prompt, and here's what this thing returned, and I can do a text similarity to see, oh, did it get me what I wanted?
Okay, cool.
But any thoughts? Putting you on the spot. Have you even thought about, gosh, I'm going to do an agent-based simulation? You signed up for the course and you thought, I'm going to do a simulation. Is that a fair statement? I'm going to do a project. That's fair. I mean, you thought about yours. You want to do some work with robots. And if you are able to, are you on a robot competition team, or what's the deal there?
So I took our robotics programming course. Anyways, long story. I'm basically done with my degree. I have to take another course this semester, so I'm taking something else, and I wanted to learn simulation. Get better at that.
Okay.
So it's really more of just trying to prepare myself for the future
Okay.
industry, because the industry is getting more and more into training digitally before you ever even build a robot.
Yeah. And we think a lot about robotic agents, obviously, because they are going to become more and more in our world. But my sense is that the disembodied agents, right? Robots are agents with a body, but the agents that are just purely software agents, I think they're going to far outnumber the robotic agents. because I can make a million of them in a minute, right? Whereas with robots, I can't even keep 100 of them running at the same time. So you may want to think along those lines too. Just how do I have agents that are trying to share some resource? Now you can do that with the robots actually. Long ago, I did some simplistic experiments with a team, and what we were studying is if you got a bunch of robots in a room and then there's only one door, how do they get out of the room efficiently without all running into each other and killing each other, right? And that sounds like a robot problem, and the way we framed it, it is a robot problem. They were all UAVs, so if they ran into each other, they would crash, right? But if you think about it, what's happening is we were trying to explore how those robots, those independent agents, without anybody being in charge and without any human oversight, were sharing the resource, which was the door. So if you abstract away from, hey, I want to get all these robots out of the room using the door, and instead say, I've got a bunch of software agents and I've only got one resource and I need them to share this resource in the most efficient way. Now we're talking about a lot of problems. Communication channels, bandwidth, printers, all kinds of things. So you can say, hell, here's my specific simulation, but oh, by the way, this other work or future work, this relates to blah, 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 blah. Anybody else? Did you think you were going to do a project? Let's start out there. You thought, yeah, probably. Garfield's probably going to make me do a project. And then did you think, I'm always interested in X? Nope. Okay, so by tomorrow, let's have some discussion about that so we can start to frame that, because tomorrow is Thursday and then I don't get to see you till Monday, and then Monday we're going to have the first assignment due where I want you to propose, hey, this is what I want to do, and I'll give you some more examples in a minute too.
So the idea of all the UAVs trying to go out the door,
Yeah,
is kind of interesting to me. Would it make a difference if you were to put them onto teams and then have the teams try to share the same door to see if they
Yes.
get aggressive
yes,
with the other team?
yes. Yes, that would make a difference. You could explore that kind of thing. And that's actually brings up, let me mention two more things. By the way, that thing's called the opera problem because it's modeled on when people are sitting watching an opera and then intermission comes, everybody goes out into the lobby and they get wine and cheese or whatever they do at opera, and then they go back in, but they're all sharing that door. You've experienced this. You've all been to the movies. And then after the movie was over, you notice how everybody left and shared the door in a reasonably efficient way and nobody got into a fist fight probably, right?
Apparently you've been before long enough.
So,
I'm tired, so my jokes.
well, my wife's like developed theater phobia, right? She's like, I'm not going out in public anymore. And this so to the theater.
Like, along the same lines, I got interested with that. What about what about having them try to figure out the boundaries of their environment as a team?
Yeah.
Like, how can we more efficiently map?
That's a great, the mapping problem is very well studied. It's a great problem. One version of that is, there's all kinds of versions of that. One is, here's some just terrain we need to find the boundaries of. One is, we've got toxic cloud. How can we find the edges of toxic cloud? It's a similar thing, but now the boundaries can be shifting over time too. But yeah, that's a great one. And there's all kinds of boundary detection and surveillance kinds of problems. So one would be, we need to surveil this space with a whole fleet of drones. So initially you would just space them evenly, but it might be that space isn't evenly distributed in terms of interest. So you might want more drones over a more interesting place and less, or you might want it where all these drones are flying around and then when one of them spots something, then some other ones come in. Or if you really want to get complicated, some drones have a certain suite of sensors and some drones have another suite of sensors, and a drone sees something and calls to somebody else and says, hey, I don't have the right sensors, you do. You know, come over here. How do you make that happen? So there's a million variations on these things. To go back to what you were saying about teams, another version that's been studied a fair amount, and I've had a couple students work with this, you know, with all different levels of success. I call it the altruism game. So you have just what we call flat world, right? Flat world in the simulation community means it's a 2D space with no hills and no obstacles, no walls, none of that. It's just flat world. And in flat world, vegetation grows, right? So you have some kind of a vegetation growth rate. And then you have these agents that walk around and they can only survive by eating the vegetation. But they can carry more than they need at any point in time. So if they gather up a bunch of vegetation, they can carry that vegetation through the places that don't have any until they get to somewhere else, and then they can pick up more. Okay? So what if I have a bunch of vegetation and I come across you and you're about to die because you don't have any? Should I give you some of my vegetation? Right? That's the altruistic part. And so you can start that game out in a nice simplistic way where the agents are just unidentified. But now what happens if you put them on teams or tribes? Oh, I could be altruistic within my tribe, but I'm not altruistic between tribes. That kind of stuff. It'd be really more complicated if you got into we're going to combat, right? We're going to steal resource from other. That's more difficult, but you understand the idea and how. By the way, these guys can get complex really quickly, so we have to find the right balance.
It just reminded me of a simulation. I mean, obviously we're in simulations, but basically they were just spheres, and you could give points, you could take points, but it was slower than giving points, and you could stockpile points, and that was like hit points. And it ended up being that there would be the ones that would give points evenly amongst themselves involved, because each one had different values for how much points they want to keep and how loyal they are. That the ones that would want to give points away versus trying to take points would end up, those ones that they tried to take the points would eventually get like basically killed off because it is something that's kind of simulation.
And again, notice the behavior you're describing, the individual behavior you describe, but what's the effect on the community at large? Very difficult to predict. Like, who would have predicted that the one giving them away has a better survival rate than the one taking, right? That very difficult to predict, very difficult to model. By modeling, I mean, describing in a non-natural language way, like a mathematical model, right? Like, who's in mechanical here? Somebody's in mechanical engineering. That's your case. You're mechanical. Yeah, so you had to take all the strength of materials courses, and here's a beam, right? It's a cantilever beam, and so that behavior is well modeled, right? We have mathematical formulas for that kind of behavior, and we understand it quite well. But the interaction, the emergent behavior that you get through the interaction with the agents, that's the stuff that's really hard to model. I've never seen anything that was less than horribly ugly with a lot of matrix math. So yeah, the altruism. The opera problem. Oh, another one. Actually, I had a student do quite well on this at a sophomore level a few years ago. And again, it's been well studied. So if you're in the CS528, you probably don't want to publish with this, but it's you've got 100 villagers, and how many of them should be caretakers of the village, and how many should be farmers, and how many should be hunters, and how many should be protectors, that kind of thing. And you evolve basically over time a good ratio where the good of the whole is really the best thing that happens. And again, within the altruism game, you measure success by how many agents total survived. And so the idea behind altruism is I'm doing a behavior that may not benefit me directly, or in fact may even harm me, like I'm giving away my food. That may be harmful to me in the long run. But in terms of the global tribal health, we're doing a positive thing. And geneticists in the biological world study that too. I mean, they talk about how you can develop, traits as you go through the parent-child bloodline, but then they talk about, but then there's also behaviors that animals will show that where they'll protect relatives. They're protecting a similar genetic bloodline, right? But it's no direct benefit to them because they're not passing on their genetic material directly, right? but they're passing on similar genetic material through their relatives. So all kinds of games you can play with that. Another one, which I've never had a student pull this one off, is to create what's called a fuzzy cognitive map. And the reason that I think first of all, students are generally not interested in fuzzy cognitive maps, but I would really like to have a tool that I could use to play with them, and I'm too busy and lazy to build it myself. So the idea behind a fuzzy cognitive map is you have nodes. So here's a node and here's a node, and the two are connected with an edge. You know, so it's basically a graph structure, graph meaning nodes and edges. So the two nodes are connected by an edge. And then you have a relationship between the nodes. And in the simplest form, each node has a value. And in the simplest form, the relationship is either positive or negative with some kind of a ratio or some kind of a weighting. So if this one, the value goes up and it's a positive relationship, then the value of this one will go up too. Because this went up, this one will go up too. And you may have a weighting factor, like if this goes up 10, this might only go up 1. Or if this goes up 10, this might go up 50. Well, this one's connected to something else. So now that it's gone up, it's going to affect another node. And again, that node will go up or down in value. And then because that one changed, another node will go up or down in value. And if you make a great big loop back to the original node, it may be going up or down based on the reactions that it's getting from its neighbors. So that's what the math model is. Why would you use it? The simplest example is the vegetation rabbit wolf, right? So you have all this vegetation is growing, there's hardly any rabbits around, so they're not eating the vegetation, so the vegetation is growing, which means now the rabbits can now breed because there's food, right? But now that you got a lot of rabbits, the vegetation is going to go down, but the number of wolves will go up because they get to feed on the rabbits. So now that the wolves go out, then the rabbits go down. Now that the rabbits go down, the vegetation will come back. If the vegetation comes back, the rabbits come back, right? The rabbits come back, the wolves come back. Right? So you see, it's like a sine wave of 3 sine waves, each lagging the other. That's a simple way you can think about a node with a vegetation, rabbit, wolf, and how they affect each other. And there's a loop. Yeah.
I thought the problem with those simulations is the wolves would have if the success rate of the wolves hunting the rabbits, if it was too high, like they could kill them too quickly.
Yeah.
What ended up happening is one food source,
Right.
usually the rabbits,
Right.
would get wiped out when the wolf population.
Right. Right. Yep. And so and that's what you play with those models. You don't do like individual wolf, this is a good hunter, this is a bad hunter. You don't do any of that stuff. It's just, here's a node that says wolves. And then you're right, there's a weighting factor. If the wolves go up, the number of rabbits is going to go down, but what's the weighting factor? And so if it's too high, then they kill the rabbits really quickly and then they starve, right? And if it's too low, then the number of rabbits just overwhelms everybody eventually, but they'll constrain themselves because they'll eat too much vegetation and then they'll start starving off. Right? So, but that's the when I say, you know, you're going to do some experiments, that's the kind of thing you can play with and instead of you might do a specific model just to make sure you're showing the tool works, but creating the tool by which you can create the fuzzy cognitive map is actually the real goal. And all you're doing with whatever specific thing you're playing with is you're demonstrating the use of the tool. These kinds of things get done in different areas where it's difficult to try to address what the impact of a specific policy change might be. And that's where you'll see this kind of thing. And for some reason, the early literature of this, it was always about, should we increase drug interdiction at the border? Okay, if you increase drug interdiction, the number of drugs goes down. And if you do that, then the number of tourists that come to your town goes up. So now the town has more money and it can pay for the drug interdiction. It was this weird model. But you can make anything you want. One of the things that I had not seen that I think would be interesting in a fuzzy cognitive map is they always have linear behavior. So no matter what the values are inside the node, the ratios are always the same. I think it would be kind of neat to interject just before you get into the node, have an agent there. And that agent's like, okay, everything's normal, come on through, we're gonna do the normal weighting factor. And then you might have, once we get to a certain either rate of change or value to the node, then that agent may change its behavior. And the reason I would think that would be interesting is because these models are not good at predicting like panic situations. There are times when the whole structure of a network can just fall apart. Right? You may have heard the term black swan event, or in a market when the markets crash. Why do markets crash? Because for some reason people get spooked, and once people get spooked, they're like, "Oh, that guy's selling all this stock. I better get out," and everybody panics each other. With the advent of so much automated stock swapping, doesn't seem to be quite so severe. Plus, they put triggers in. If you fall a certain percentage, they're like, okay, nobody's going to sell any stocks anymore for 15 minutes or whatever. Yeah. But the fuzzy cognitive map can explore all of that stuff. You see that again, it's generally about policy, or it's about ways that ecosystems play together. One of the things that we saw with COVID was, nobody knew how supply chains work, and it was just turns out they're easy to break and hard to rebuild, right? So, but basically that was a whole node system there where you were just kind of plucking pieces out, right? You're radically changing some of the values. Similarly, a supply chain model would actually be a good model too, and that can be agent-based. Each agent can choose to purchase or not purchase, or produce or not produce, that kind of thing. And again, that would be a node-based system. You can do everything in the abstract. You can do things in a very abstract way. You can get a lot of interesting results that apply to different places. So be thinking about these things overnight. Go online, play around, see what kinds of things you can come up with, what might interest you. And again, think about now, oh gosh, I got to do a model. Here's a model. What interests you? What would you like to spend 6 weeks with? Because you're going to spend 6 weeks with it. So don't pick something you hate. Discussion about project. Anything else? Okay. Who won the game of chicken?
That's kind of, we earned, to be honest with you.
Left or right?
Both my pilots were buried.
Left or right, or was it up or down?
We broke right.
Okay. Is that normal? If you're going head on, both sides are supposed to break right? Yeah. All right. Let's get into then some of the topics. Let's see here. What is an agent we talked about? What's a modeling and simulation class, at least for CS350?
Somebody's walking the bus.
Oh, is that what it is? Huh. Let's start with the basics then. Modeling and simulation. What is a model? Have you ever used a model? Used them, right? Again, your cantilever beam, you apply 100 pounds on the end, you can predict the deflection and the stress and the strain. That's a model. That is a model. Whenever you had, let's see, what classes are we taking? What other classes are you taking that require some kind of analysis? Have you taken so far?
I can't think of any.
What's your degree program?
Computer science.
Oh, computer science, okay, yeah, okay, so you didn't do anything in the physical world, right, okay. Right. But you had to do, Becky, have you do a flow chart?
Yes.
There you go. That's a model of the software, right? That's a model. It's not the software, it's a representation of how the software will work. Yeah. And what's your degree from?
Same thing.
So Becky also make you do flow charts?
Yeah.
We need to have you guys do algorithms, by the way, so. But that's a model, right? Mishari, what degree program? Electrical. Okay, so circuit design?
Yeah.
Yeah, so someone hands you a circuit and says, what's the current through this resistor? Did you build the circuit? No.
Not yet.
You may,
Outside.
you may have in a lab, yeah. But did you have to build the circuit to answer the question? No. Why? You have rules, you have analytical techniques, mesh analysis, right? Oh, okay. That's a model. The analysis that you're doing is a model of how a real world circuit works, how the real world electrical batteries and resistors and wires work. Andrew.
Yes. But probably more of SC300 is where I use models.
Okay. How so?
My
was-
project was airplane seating.
Okay.
And so coming up with the different ways to board a plane.
Which is also widely studied. Yeah, this was with Ty Nishad or someone else.
Yes.
One of the professors in College of Business, like 15 years ago, won an award from Boeing for modeling efficient ingress and egress from the planes, right? I think I saw one of your reports when I was looking through this. So I teach that class now, so I was looking through all this old stuff. And what degree program?
Engineering physics, so all the time.
Oh, yeah, okay, so give me a model.
Well, I'm doing plasma physics work right now, I'm using Poisson's curve.
It's a model.
You do electrical stuff.
Mhm.
Kind of leave the curve.
And what are you doing now? What's the show about you doing?
I'm doing my PhD now,
Yeah.
but before engineering before, so all of the diagrams, like design and analysis diagrams, all models,
Right.
also ML models, but those are different kinds of models.
Yeah, in software engineering, we build use cases and we do flow diagrams and we do transition diagrams. Those are all just mathematical models of how the software is going to work. Or in terms of a hardware software system, how the software works. We have a class, we don't teach it anymore. It's called SE410. And I used to teach it. I really liked the class, but it wasn't worth 3 credits of your time, of your money, right? So, but it was all about modeling complex software hardware systems. Yeah. Okay, so now that we've all discussed that we've done models, what is a model? You should always know what you're doing, right? You've done it, so what is it? What would you say a model is?
It's an abstraction of some real thing. It's like the highest level term. So like for software, if we want to do model counting or something on the software, we build an abstraction of the real software. We call it a model and then run that against properties, check if
Right.
the system actually adheres to them.
Right, yep. I can't remember, did you take SE410 a couple years ago?
No, I learned it all
But-
through research.
Yeah, but it's called model-based model-based verification, model-based validation, model-based Q&A. It's a real big thing in software these days. And basically what you say is the software is in this state, and here's, this is on, this is off, this is off, this is on, whatever. And then you say, here's all the stuff we can do to the software. And every time you do something, it goes to a new state. And the idea is starting from this nice, good, safe start state, do you ever get to a bad state? Think about traffic lights. Are the lights ever all green at the same time in all directions? That's bad, right? So that's called model-based. And yeah, so the model is an abstraction of the real world. And the degree to which the abstraction is done depends on what you need from the model. So Mishara, you said you were doing circuit analysis. If I gave you a simple circuit and said, here's the voltage, and here's a resistor, find the current through that resistor, right? The model is never as complete as the real world. You always make assumptions in the model to simplify things. So in that case, what are some of the assumptions that we have? In the case of the solving an electrical circuit, which I guess most of you guys, or a bunch of you guys, what's some of the assumptions?
It all works.
All right, that's a good one. What else?
No.
Right, the wire has a resistance of 0, which we know is not true. But it's right, it's engineering, right? You don't have to be right, you have to be close enough. So yeah. We also assume that the resistor, even though it may get hot in the real world and change its resistance, we assume that it's constant, right? That's again, it's generally a good assumption, but it's not a technically correct assumption. All models are that way. You didn't consider the weight of the circuit. You didn't consider how it smelled, right? It's not in the model. We're licking the battery terminals. If you're my age, you used to have to test your battery by licking the terminals. So that's what a model is. It's an abstraction. Now, how abstract? How close does it have to match the real world?
Depends on how you-
Completely depends on what you're trying to do. Exactly. So if I want to have, I'm going to do a fuzzy cognitive map of, the pre-World War I Europe. Here's Serbia, and here's Montenegro, and here's Austro-Hungarian Empire, blah, 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 blah. Okay, Austro-Hungarian Empire, 80 million people, 1 dot, right, in my model. You can have really high levels of abstraction. If you need to, then you start to make your model more and more detailed. It depends on what you're trying to do with it. That term, by the way, it's a horrible term in modeling and simulation. It's called fidelity, the fidelity of the model, meaning how granular it is. And that term fidelity has absolutely no common accepted definition whatsoever. So we'll often talk about the fidelity of the model, but be aware that when people are talking about that, you can't say, well, how do I measure it? Like if I have 2 models, how do I measure their fidelity? I don't, because I don't have a good definition for fidelity, but the term is used all the time. So that's what a model is. And you've all used models like crazy going through school, right? Solving things on pen and paper, claiming that that's how the physical world would work. You're working a model. What's a simulation then? If that's what a model is, what's a simulation? When you think of a simulation, you get any images in your head? Kind of abstract, right?
I mean, I can think of different ones, like there's I get the plane one where it's just the dots turning off and on. So
Right.
little dots moving across the screen.
Okay, good. Dots turning on and off, dots moving across the screen. Anybody else got something they're visualizing?
And I've got more advanced one in the box where you literally see the robot take off, fly around the room.
Right, yeah. There was some video games now, they spend a lot of money just on great visualization, right?
Like it gives you an output, gives you data.
Okay, maybe, if you built it right. But how? What was common to the 3 things that he mentioned? Lights turning on and off, dots moving across the screen, robot moving around the room. What's common here?
They were dynamic.
Exactly. So the model is the representation of the real world thing. The simulation is the model being exercised. The simulation is the thing where the model is placed in some kind of an environment and then it reacts to that environment or does something to the environment. So as a general rule, every simulation needs two things. It needs the model of the thing that you're studying, but then it also needs an environment for that thing to operate in. And then that simulation will somehow produce changes in state or motion or changes in behavior of that model over time. And there's different ways that that can happen, which we'll run through some definitions in a minute. Okay, so that's the basics, right? So when in this document, when I'm saying you've got the research question, then you've got background. In the background, you're pretty much discussing the real world situation. You're not discussing your model yet. You're discussing the real world situation that you want to investigate. And then when you say go into the model and simulation design in this section, you describe what the real world is that you want to investigate. And then you say, for the model, I'm going to represent the real world this way. It's a finite state machine with transitions. It's a whatever. And the simulation is going to contain, right? I'm going to model a wolf pack. Okay, but there's no sound, okay? We're not going to have to listen to howling from the simulation. There's no smell, okay? All we're going to model is how they interact with each other. Oh, okay. Dominance hierarchy among wolves.
Well, I'd say that's not how Wolfpack actually works, but
They have rules, though, based on a societal structure, right?
just not the Wolfpack model that you're describing, because that was based on wolves in captivity, not wolves in the wild.
Oh, I see, yeah.
And so they have a much more dynamic interaction than what you're describing. It's not hierarchical. It's usually the hurdle.
Oh, so that what they used to call the alpha male is really the highest ranking female. Tends to be. A lot of antisocial animals seem to do that, right? Elephants are very maternal too. Yeah. There was a guy named what's his name from MIT. I worked with him for a little while. He did his PhD thesis on imposing dominant structure on agents to see if that would help them become more efficient. And he used the wolf pack dominance hierarchy as a model. And so he calls it alpha wolf. We should be able to look him up. And he created software where you start out as a wolf pup and you grow and you can become more effective or more dominant in the wolf pack based on your behaviors as you grow. And the way that you influence the other wolves is by howling into a microphone. And he said adults were horrible at this because he'd go to a conference and put this thing out and the adults were too embarrassed, they wouldn't do it. But he said, then you get a 10-year-old kid in there and he's like, king of the wolves. So, model and simulation. That's what you're going to put in there. Here's my model, here's my simulation. And you can say, it's common to leave stuff out and everyone's like, yeah, you should have left that out. That doesn't make any sense to keep. But it's also common, you're going to have to make decisions about what to put in your model, what to keep out of your model. And it's common here to say, we're explicitly not considering X. We're explicitly not considering the weight because it didn't contribute to, or the color, it didn't contribute to. I'm doing a traffic study. I'm not including the color of the cars because it doesn't matter in what I'm trying to do, right? By the way, traffic studies, also good agent-based models. They're a little hard, they're harder than you would think to pull off though. And the reason is designing the routes is actually tricky. They used to do traffic models like particle flow, like everyone's just molecules of water in a pipe. And those were not predictive of real world traffic very well at all. And then they started to look at, oh, wait, drivers actually are agents. So let's have, instead of molecules of water going in a pipe, let's have a bunch of agents on the road. And generally, they were getting better traffic models. They can produce things like, have you ever seen this? You go down the highway and then it gets really slow. And then you get down the highway and you're like, oh, there's going to be an accident. And there's nothing there. And this whole wave, the wave can show up for basically no reason. It might have been that 20 minutes ago, somebody put on their brakes real hard for no reason, or they saw a raccoon or something, and then everybody else slowed down, and then that just created a wave, and now it's like a standing wave that you're going through, right? So you can model things like that. I've not had a student. I've taught CS225 for a long time, and I got lots of students, but I've not had a student do what I thought was a really good traffic model. I have had students try to do like pedestrian traffic around campus, but modeling the paths is non-trivial. All right, so let's see. Here's our rough schedule. This is just a draft, so it's going to change. This still shows this due here, but I moved it here because I was yesterday. Move that here and also gives you a little more time. I think you guys need another day or two to incubate. And then after that, it's basically every week. Boom, 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 right through the project stuff. These are all P1, P2, P3. Now I switch that. And then the homework you do, they don't start for another week. So that was already posted. I haven't posted any of the others, but that's our rough schedule, right? And then obviously it can be fluid. That's when that gets more solidified, I'll post a version on, I'll post the updated version online. All right, so we did all this. And we've gone through definition of models. So my notes, I put together these notes quite a few years ago, actually. And the notes, for the most part, are nothing but a bunch of definitions. Like, I don't know, there's 60 or 80 definitions or something. And the reason I did that is my wife, a long time ago, told me something that I thought was very clever. She said, you know, if you go to the back of a book and you look at the index and you look at all the terms in the index and you can say something reasonably intelligent about each one of those terms, you know the whole book, right? That's what that means. So I'm giving you the book in index form, right? In definition form. And when I say the book, we don't have a text, but yeah. Okay. And then, you know, why do people do these simulations? Understanding, predicting, analyzing, training. And what are the benefits? Cost, exploration of what ifs, right? So let's say you wanted to do, you want to do hurricane prep. Here we are, Volusia County, we want to make sure we're ready for a hurricane. We would need to understand what the effects of a hurricane are if it was at this level and it came in from this location, you know, from this location at this angle, blah, blah, blah. Well, we're not good at creating hurricanes at will, right? It's not like we can just whip one up and send it in over Daytona Beach. And it would be ethically questionable to do so, right? So what do? Simulation. And the time frame when I was growing up, we talked a lot about being blown up by an atomic bomb, because when I was growing up, we were always 15 minutes away from being blown up by an atomic bomb. You ever seen those duck and cover drills? I did those drills. So that was kind of, you know, top of mind. And, you know, they did a lot of experiments where they actually blew up atomic bombs. And they did a lot of experiments where they put some soldiers in trenches and blew atomic bombs, and they didn't tell the soldiers that, oh, you're going to get cancer in 3 years, you know. The degree to which they didn't know and didn't care is iffy, right? They took captured ships, put them out in the middle of the ocean, and dropped an atomic bomb on them. Or old ones. Or old ones, yeah.
Sorry, some of the ships that I believe should have been in museums were utilized and such.
Yeah, it's a rather destructive. Gosh, what the heck? Back then it was like, we have so much stuff, we'll never run out, right? So that's one of the reasons, obviously, that you would do the simulation. Either you cannot replicate the real world event, or you really don't want to replicate the real world event. So you can explore all these ones. And then, of course, there's cost. They built for research and for the AE department, like a $10 million wind tunnel out behind Michaelplex. Really nice wind tunnel. we could have had a digital wind tunnel for like $100,000, right? So a lot cheaper. And you can reconfigure it a lot easier, right? But then people always wonder about, oh, what's the fidelity? Does it actually work for the real world? So you do get cost benefits. And I think you were mentioning nowadays people are doing lots and lots more of digital development, digital design, digital testing, and then you go to the real world. And yeah, that's happened. Partly because the modeling and simulation tools have become better, partly because computers have just gotten faster, cheaper, so much memory, so many processing cycles that we can do things that you could technically have done them 40 years ago, but it would have taken a lot longer for the computations to run. The tools weren't there and the physical machine speed wasn't there. Why do we do these things? Understanding, predicting, analyzing, training. So understanding, let's start with predicting. I think that's what people do think a lot about. Oh, I want to run these systems and then I want to get some experimental results, and that way I'll understand how the system works. That's a goal. And from there I can predict results, right? If I do this, if this happens to the system, I can predict that, this is what the result will be. We also do it educational purposes, right? So training. The militaries around the world invest a great deal of money in digital or cyber physical training devices. There's a big warehouse in, I think, Omaha, and you go in this big warehouse and there's a bunch of boxes. And if you go inside one of these boxes, you're basically inside of an M1 tank. And when you look out the little portholes, it looks like you're in, Fulda Gap or something like that, or Fallujah. And the next box is another tank, and the next box is another tank. Oh, and they all get to play in the same virtual space. And some of them get to play the blue team, some play the red team, right? And then they'll have different versions, for different kinds of vehicles. And then those guys might be hooked up with, I think they hooked them up with Air Cavalry in Texas. Is there an Air Cavalry unit? There's some First Cavalry Division or something like that. Helicopters. They hooked them up with them digitally, and they could all play in the same virtual space. Well, first of all, that's great training. We have some issues, but that's good training. Secondly, that sure is a heck of a lot cheaper than dragging everybody out to Arizona, throwing them out in the desert. The initial cost is really expensive, right, to build all that infrastructure, but the reuse that you get back from it is good. By the way, I said there's some iffy with the training, and the reason is some of the training that happens, you get people doing things in a simulation that they wouldn't do in the real world, because they know at the end of the day in a simulation they get to walk out and go home and have dinner, right? Whereas in the real world, you can't predict it. And then analyzing. Same trick with analyzing. That's what you guys, your circuit design, analyzing, box beams, right? All of your, whatever you do in EP, right? Analyzing. So. Okay, so let's walk through some different types, and then I think we're good for the day. Let me know if you've heard these terms before. Finite element modeling. What's it mean? Anybody? It's on there.
At least for me, it's where you're basically taking a structure and then you're breaking it into small parts. Each parts have a certain amount of connection between each other, and that's how it can be squares, it can be spheres.
It's kind of like, and I'm going to approach it from the opposite direction. It's almost like you have digital Legos, and what you're doing is someone gives you a square and a circle and a sphere and a rhomboid and a triangle, and your job is to put them all together to create something. But the thing is, with each of those individual piece parts, they have well-defined behaviors in terms of there's a model for how a flat square plate works. There's a model for how a cylinder or a sphere works. And by works, I mean how it affects how it transmits load. If you put a load on one corner, what does it do? And then once you put all those together, what you end up with is giant matrix. And then you use these different matrix solution techniques to come up with, okay, I've got another matrix that describes the forces that I put on this structure. And then I can come up with a resulting matrix that tells me how much the strain was, and I can figure out how much how much stress and strain I put on this thing and how much it displaces. In a dynamic world, I can figure out resonant frequencies, and I can figure out what frequencies it's vibrating at, that kind of stuff. This has been around for a while. Nastran is, they use this in the AE community here. Our AE students use Nastran in their finite element modeling course. I don't know if any of you guys else have used Nastran. For the double E's, we don't use it, but SPICE is the equivalent. It turns out, once you make the components into a matrix, you don't care where the matrix came from. It's the exact same math. So in terms of the electronic version, you know, they have resistors and voltage sources and capacitors and all this other stuff. And there's basically a functional equivalent to all the mechanical things in the world. So they can, just like it was a mechanical system, they can create they can create the matrix for it. The thermal people do the same thing for thermodynamics. So that's the basic approach. You have these basic elements that are provided to you, and you construct your model. Now, you actually do it in the process you described. I have a structure, and I'm going to carve it up into these standardized pieces. On my first job with McDonnell Douglas in the 80s, I was using Nastran and doing that to some spaceflight hardware, right? Doing stress and mechanical analysis. Then we get computational fluid dynamics, CFD. This is a highly computationally intensive activity. So you tend to see like that Zeus machine or whatever it is down in the corner, the one with all the nodes. What's it called?
Vega.
Vega, yeah. That's those kinds of machines get used for this stuff. Lots of computation. And the trick here is, in order to get a better, think about it, what you're doing is you're breaking the fluid up into these little piece parts and or particles, but generally little what we call control volumes. And then you're looking to get at the boundary layer. So you have to show that like momentum of the fluid is conserved as you go from one control volume to another. Energy has to be conserved as you go from one boundary layer to another, that kind of thing. So by having those things be restrictive, you get a model of how fluid flows through the system. Now think about it. Fluid itself has no boundary, right? It's just fluid. So the degree to which you get better accuracy depends on how good you've made these control volumes. Well, it turns out generally the smaller the control volume, the better. But the smaller the control volume, the more of them there are, the more of them there are, the more computation there is. You get a restricting factor. I don't know any tools for that off the top of my head. However, I know they're out there. This is a well-studied and used technique. The EP people used to use this stuff for something, and I don't know what, but I know I've met some EP students that were using, before we had this, we had a Beowulf cluster. They were using the Beowulf cluster.
Even MATLAB can do it now.
Oh, yeah.
Like you can do that MATLAB solid work. You can do it almost any 3D software now. CFD is also, you know, finite element analysis is all. I would imagine.
By the way, in SC300 last semester, I had a team of AE students build a small finite element tool from scratch, and they actually did it. I mean, they did a good job. It's pretty cool. And I'm like, you need to show this to your professors, and maybe they can use it. But then they all graduated, so they didn't care. But yeah, and I'm wondering if how that actually may play in with all of the animation software. I don't know the animation tools that well, but it wouldn't shock me if they're using some of these techniques. You know, it used to be like water looked like crap in an animated world. Now it looks great, right? So they do a different thing with skins though, right? So they do a framework and then they put skins on it. It's fine. It's not finite element in the sense of
only
that.
only a couple of games like use actual particle physics. Most use a spline base with a basically it's a spline that says, hey, the water's moving here, there's multiple splines with different times.
Got it. So it's a path. They're giving it a path, right?
But I think, Star Citizen does it, there's a couple other. I don't remember any of them. Star Citizen's the only one I actually does particle physics.
Discrete event simulation. This is not intuitive. Most simulations operate through time. Like we said, the model is the abstract version of the real world thing. The simulation is the model operating through time. And what most people will do is they think of time in a continuous way, and you say, okay, we're going to go through and update our models that are existing in the simulation. And each time we go through and do that, that's in the real world, a tenth of a second, or it's 10 minutes, whatever. And that's generally called a tick. And that's a very intuitive way to run your models, where you just keep doing a loop and you ask each model, hey, here's your situation. What do you want to do? Here's what I want to do. Okay, you've done it, Then you go through and you do it again. That's a very intuitive way. However, if there are situations where you go long periods of time where not very many things are happening, that's not a very computationally efficient way to run a simulation. So instead, you can do a discrete event simulation. And basically what you're doing is you're saying, you know what? Nothing's going to happen. We can keep doing our loop over and over, but nothing's going to happen for, 10 minutes of simulated time. So instead of just going through this loop, why don't we just set up an event and say, okay, the time is 10 minutes from now, and here's when an event happens. And then we can just jump to that event. And then we can have another event 10 minutes later, or another event 2 minutes later, or whatever. And so basically what you're doing is you are not doing a continuous time where you're just looping through and looping through. Instead, what you're doing is setting up a schedule and saying, this event happens here, this event happens here, this event happens here. And the places where you tend to use these kinds of styles is in service-based simulations. So people study queuing models a lot. Okay, I go to the bank and I get in line. The way you might do that in a discrete event simulation, the way you might do it if you do continuous time is you loop, you loop, you loop. Did a customer come in the door? Nope, 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 nope. Okay. So instead you say, okay, it's it's 10 o'clock now. At 10:07, a customer is going to come in. So you put that on the schedule, and then your simulation jumps to 10:07 when the customer comes in. At 10:08, they're going to meet the teller. Okay, we'll jump. So this is what I've simulated. It's a discontinuous time, discrete event. And what you're focused on is not time, you're focused on the events. And generally, you don't have all the events predicted ahead of time. Generally, it's the kind of model where you're saying, you know what, customers come up to my shop at an average of 4 to 8 minutes. And so I have some kind of a random number generator between 4 and 8 minutes, and that's the next scheduled event. It takes me generally to service a customer 8 minutes, plus or minus 3. Okay, so then I've got another random number generator to schedule that. Elevator models also do this. For an elevator, it doesn't know when someone's going to show up on the 14th floor and request to go up or down, right? This little elevator can't predict when the next. So in large buildings, the question is, what should an elevator do? Like, where should an elevator hang out when it's empty? If it's not being used, where should it hang out? Or if there's a sequence of calls, what's the best sequence to service those calls? Those kinds of questions. And in large buildings, that's actually a interesting problem, because it can really affect the quality of service that you're providing to people simply wanting to go up or down your building. Technically speaking, it's one of the limiting factors for the height of a building, because the higher a building, the more people you need, the more people you need, the more elevators you need. And after a while, you have all elevators and no office space. So weird things like that people predict, right? But within the context of real world buildings, that's actually something that people study. How many elevators should we have? And then they, of course, boil that down to some kind of civil code. Okay, you've got this much population, this many floors. By law, you need to have X number of elevators, something like that. Elevators today, by the way, are getting smarter because AI is everywhere. So now some elevators can be installed in a building, and over time they actually learn the patterns, and they learn the next most likely place I'm going to be. Call that. So if I'm empty, I'll go to that place because it's probably where someone's going to call me next. You can think of some of that simplistically. Like if you were a hotel elevator, you know that in the morning, you probably should be on the upper floors because everybody wants to come and go down and leave, right? Or go to breakfast and then leave. And you know, in the afternoon, you probably should be, in the evening, you probably should be on the ground floor if you're empty because probably people are coming in and want to go up to their rooms. So just by time of day, you can do some simple, if you were a simple thinking elevator, you could figure that out. So anyway, we'll pick up with this tomorrow. I'm going to ask you about your simulation topics again. So be thinking about that. And then we'll just keep walking through this. Do you have any questions before we go?